Hi everyone. Today we will see a very important concept, namely flux of a vector. In electricity and magnetism course, it is often necessary to calculate the flux of a vector quantity through a surface. Imagine that, for example, I want to fill a bottle, for example. I have a tap like that, for example. I have water here, and my goal is to fill this bottle, for example. Here it is the direction of the flow, and here it is the sense of flow, because here we distinguish between sense and direction. To effectively fulfill my bottle, I have to make sure that the aperture of my bottle is opposite the tap, like that. If I place, for example, my bottle like this, here I lose some water. And imagine that, and if I place it like that, I can never fill it. If I place it like that, I can never fill it. Let's try to make a mathematical relation which will allow to evaluate the quantity of water which pass through the surface of bottle. Let's try to make a mathematical relation which will allow to evaluate the quantity of water which pass through the surface. So it is our surface of my bottle. So of water which pass through the surface of bottle. First we will orient our surface. I have this surface, the surface of our bottle, and this is a normal pointed outward by convention, please. And this normal vector is a unit vector, so I use hat, so I have n hat. See the water flow as a vector field, as is like a vector field, is a vector field, for example. You can see the water flow as a vector field, a lot of vector. For example, if I consider one of this vector E, for example, I have this vector E and I have my surface like this, and my normal vector is like that. We remark that if I have, for example, my tap like that, and my bottle like this, so here I have n parallel to E and exactly anti-parallel, it is not a problem. In this case the flux is max. And in this another situation, if my surface is this normal exactly parallel perpendicular to E, my flux is 0 minimum. We see here one of the properties of dot product. So the flux is a result of a certain scalar product. So we have here our bottle and our tap. Here it is our aperture. So we can represent this figure like this. So we have the sense of our vector field like this, and I represent just one vector here. We remark that if E parallel to N, so here is anti-parallel, so parallel or anti-parallel, it is not a problem. here the flux is max. And in this situation, if we have my bottle like this, and my tap like that, I cannot fulfill my bottle. I can represent this situation like this. So we have my vector E like this and my normal vector like this. So in this situation, we remark that E perpendicular to N. In this situation, the flux is 0, minimum. You can see here one of the properties of dot product or scalar product. We can tell dot product or scalar product. The flux is the result of a scalar product. Right? Phi equals E dot S. This S is our oriented surface, so this surface is like this. So is oriented like that, equals S n hat. But this expression is only available if E is a constant. To generalize this expression, we consider a very small surface. So we consider, for example, here a very small oriented surface called ds. So in this situation, we have elementary flux d phi equals a very small flux equals E dot ds. And if I want phi is quite simply double integral of d phi surface. We have here double integral because we have a surface, and you know that surface has two dimensions, so I use this double integral. Equals E dot ds. So it is the expression of flux of a vector through this surface S. In this situation, if I have E constant, I can put this E outside of this integral, so I have E dot double integral of dss, and this double integral is exactly S. So finally, I obtain phi equals E dot S if E a constant vector.